In this video, we'll talk about the idea of subspaces of a vector space and spans of vectors, two concepts that are needed to go further into the ideas of linear algebra. So if I have a vector space V, in this case you can think of any vector space sort of in the abstract math sense, or if you want a concrete example, something like our normal two-component real number vectors, or three or four, whatever number components you want for real number vectors. A subspace W is a subset of V, so it's some collection of these vectors. It has the following two properties. If I add together two vectors in W, sum stays in W. And if I multiply a vector in W by a scalar, or a real number in the case of our normal vectors, that result also stays in W. If you think about it, these are the two main properties that define a vector space as a whole, right? What can we do with these two-component real number vectors? We can add them together, we can multiply them by scalars. That's really it. And if a subset of them has the property that it's sort of closed under this operation, that if I take two things that are in W, these operations all stay in W, then it's called a subspace. It's sort of isolated and sits on its own as a sort of vector space that's inside of our original one, because it has the same properties and everything stays inside that W. And so we talk about it as a subspace, or a vector space that's inside of our bigger vector space V. As one quick example of this, if I take my V to be our two component vectors, and let W be the set of all vectors of the form A and 0 for all real numbers A, that is a subspace of V. How do we know that? Well, if I take any two vectors of this form, that's A0 and B0, I add them up, I get a number on top and a 0 on the bottom, so it fits into the form of W. Multiply this by a scalar, I get the same result. For more examples of this, we'll take our normal two-component vectors again, and ask the following things are subspaces of this vector space. If I take the entire space, R2 here, the entire space is always a subspace. The fact that it is a vector space means I can add vectors and I can multiply by constants, which is exactly what defines subspace as well. What about the next one? Just the vector 0, 0. This is now given a special name called the zero subspace because, yes, this is actually a subspace. And why does that work? Well, let me take any two vectors that are in that subspace. Well, it only contains one vector. So if I take any two, that means it has to be 0, 0 plus 0, 0. I have nothing else to choose from. Well, if I add these, I get 0, 0. Well, that's in that set. Similarly, if I take any constant multiple of 0, 0, because it's 0, I still get 0, 0. Both these properties mean that that one element, that one vector there, is on its own a subspace. It's called the zero subspace. What about number 3? We have vectors of the form AA for all real numbers A. For a similar reason to the example before, this also is a subspace. Let's check it out. Now I have more options. If I want to add together, I could add a vector of the form AA to something of the form BB for a different number B, because now I have different numbers to choose from. But for any of these two numbers, I can add these vectors, and I get A plus B, but that is in the same form, so it is in this subset as well. And similarly, if I multiply a vector of the form AA by a constant, I get alpha A, which again fits the form. It is the same thing on top and the bottom. So this, again, is a subspace. Now what about 4? For 4, we already know that this first part gives a subspace. You could check in a similar way, this second part also gives a subspace on its own. But putting them together, turns out I don't get a subspace. And why is that? Well, let's try to add one vector from each category together and see what we get. If I add these vectors, AA to AB minus B, so I've taken one from the first category, one from the second. If I add these together, I get A plus B, A minus B, which is not of the proper form, provided A or B is not 0. As a sort of concrete example, if I add 1, 1 to the vector 1 minus 1, I get 2 and 0, which is not of the form AA or A minus A for any number A. So this is not a subspace. Another sort of classic examples of subspaces are spans of vectors. It turns out every subspace is written this way. Might get there eventually. So if I have vectors v1 through vn, then a linear combination of those vectors is another vector of the form c1v1 plus c2v2 up to cn for any constants c1 through cn. Basically, I get to pick a set of constants, stick them in front of the vectors, add them up, and that gets me a linear combination. Now, for a set of vectors, the span of those vectors is the set of all linear combinations of these vectors. That is, it is all vectors of the form c1v1 plus c2v2 plus cn for any choice of constants c1 through cn. I can pick any constant that gives me a linear combination. If I take the set of all possible linear combinations, that gets me the span of these vectors. So just to tie things back a little bit, example 3 from above, which was this set, could be thought of as the span of the vector 1, 1. There's only one vector taking constant multiples, not really linear combinations, and any multiple of 1, 1 gets me AA for all real numbers A. Now, some facts about the span. First fact, the span of a set of vectors is always a subspace. Now, why is that? Well, if I look at what the span is, it's all vectors of the form c1v1 plus c2v2 plus cnvn for choices of constants. Now, if I were to add two of these together, I'm really just combining the constants. And so that's another vector of the same form, so it fits into the span. So if multiplied by a constant, I'm just multiplying each of these constants by that same number, and so it fits into the span as well. And 2, for a bit of terminology, in this case, the original vectors are called the spanning set for this subspace. And I guess I should go back and call this a spanning set, because there are multiple spanning sets for any given subspace, and we'll see that in our next bit of example. Now, one of the main questions you get asked about a span is if a given vector is in a span of the original set of vectors. So I want to ask, is the vector 1, 2, 3 in the span of 2, minus 1, 1, and 3, 1, 2? What's this question really asking? This question's asking if I can find constants c1 and c2, so that if I do c1 plus the vector 2, minus 1, 1, and c2, the vector 3, 1, 2, I get 1, 2, 3. That's really what it's asking. But that's just a system of equations I can try to solve with matrices. So I can set the augmented matrix, 2, minus 1, 1, 3, 1, 2, 1, 2, 3, and then try to solve this out and see what I get. So I'm going to do the row reduction, and we get to the following. We add the line back in, and we'll see that this row here says 0, 0, minus 10 thirds, which means there's no solution. So therefore, no, this vector is not in the span, because there were no constants c1 and c2 to make this work. Now, that isn't just because I only had 2 vectors for a 3-component solution here. I could actually have gotten an answer, right? If this number had come out to be 0, then I'd have a solution, and it'd be great. In particular, if I replace this 1 up top here by a 13 thirds, then I would get that it is in the span. So as an extra check, the vector 13 over 3, 2, 3 is in the span. And if you do all that work, you will get down to a 0 here, saying that there then is a solution to this problem. So that's the idea of spans and subspaces, which are concepts from the language that we'll need to do more advanced problems in this area.